Hello everyone, myself Dr. Ranjith Kumar Gatla, working as an Associate Professor in the Department of Electrical and Electronics Engineering. So in today's class, we are going to discuss about definition and terminology from the module 2, which is analysis of electrical circuits. So in previous classes, we have discussed some definition and terminology from the module 1, that is Introduction to Electrical Circuits, and as well as another module which is about the network theorems. And here we are going to discuss about the definition and terminologies from the analysis of electrical circuits. So in this course, in this class, mainly these definition and terminologies are based on the alternating quantities, because we have studied these alternating quantities in the module 1 itself. But anyway, there we did not discuss, so that's why here we are going to discuss some definitions and the terminologies which we are using in the AC quantities, that is alternating quantities. So first let us start with the form factor. So here, and this we have already discussed in the various periodic waveforms. How to find the average and RMS value of the periodic waveforms, the different periodic waveforms. So once we find the average and RMS value of the periodic waveforms, then we can able to find the form factor and the peak factor for those various periodic waveforms. Here, first the form factor. So here the form factor is nothing but it is the ratio of the root mean square value to the average value of an alternating quantity. So which means here the form factor can be calculated for the alternating quantity of the voltage or the current waveform. So let us consider if it is a AC waveform. As we know, the AC waveform is in a sinusoidal in nature. So first, if we know the value of the RMS and average value of the sinusoidal waveform, then we can find the form factor. So here the form factor, here it is, let us indicate with F form factor. So here the form factor is the ratio of the RMS value by the average value. So suppose the form factor of a voltage waveform, then here it is RMS value, or let us consider here voltage, here it is V RMS by V average. And if it is a current, this is for the voltage. And if you want to find the form factor for the current waveform, then here it is I RMS by I average. So we have already discussed what is meant by the RMS voltage and what is meant by the average voltage. But anyway, for the reference purpose, here I have mentioned what is meant by the average and RMS voltage. So here the average means the average values of all the instantaneous values of the current and voltage over one complete cycle is known as the average value of an alternating quantity. So that we have already discussed how we can find the average value of a particular periodic waveform, and the standard equation is also that we have seen. So the average value, which is equal here 1 by t, integral 0 to t into, so for the sine wave, here it is Vm sine omega t into d omega t. So this is the standard equation to find the average value of an alternating quantities. Or if you want to find the average value of any periodic waveform, then this equation will become here, it is 1 by t integral 0 to t into Vm of t into dt, right? Vm of t into dt, or in another words, so here no need to mention Vm of t, V of t into dt. So here V of t represents what kind of waveform here it is. Suppose if it is a current alternating current waveforms, then here V of t will become here Im sine omega t, and if it is a current, then V of t will become here Vm sine omega t. So like that, here this V of t represents the kind of waveform for which we need to find the form factor. So basically the form factor is nothing but the ratio of the RMS by average value of a quantity. So either it may be voltage or the current. So this is about the form factor. Next, about the peak factor. So here the peak factor is, again, here it is the ratio of the maximum value to the RMS value. The maximum value to the RMS value. So which means here the peak factor, let us consider here it is PF. Don't get confused again. PF means power factor. Here it is peak factor, which is equal to the ratio of the maximum value, which means suppose if you want to find the peak factor for the voltage, alternating voltage waveform, then here it is, let us indicate with Vm, which means the maximum value or the peak value by RMS value. Again, here it is Vrms. And similarly, if you want to find for the current waveform, then here Im by Irms. Right. So here we know already how to find the Im and Vm. Okay, for your reference purpose, let me discuss again here. Suppose if it is a one complete sine wave, then here it is Vm or Im. Okay. Suppose here this waveform represents voltage waveform, then here it will be the Vm, and if it is representing as a current waveform, then here it is the Im. So this is how we can find the maximum value, okay, or the peak value of a particular quantity. Next, the phase and phase difference. Okay, so here first let us see, okay, what is mean by the phase and what is mean by the phase difference between the two quantities. Okay, so here as we know, the AC alternating quantities are representing in a sinusoidal waveform. So suppose if there are two alternating quantities, let us consider voltage and current. Okay, fine. Here let us consider here this is the current waveform. Yes. So here it is the current waveform. Okay, but let us draw the voltage waveform also here. Okay, so let me draw the voltage waveform here. So here right. Okay, let us consider this is a voltage. This is voltage waveform and this is the current waveform. So here as you can see, the phase difference between these two. I mean, how we can calculate the phase difference between these two alternating quantities. So here, as you can see here, the voltage is starting at the 0 degrees, and but here the current is starting. Okay, so before the 0 degrees. Okay, and then the phase difference, which means the phase difference between these 2 points is, let us consider phi, and then here it is the distance. Okay, the angular distance between these two is called as a phase difference. So these phase difference can be calculated either the difference between these 2 points, or either the difference between these 2 points, I mean the difference between the two peak points, or either the difference between these 2 points also, like I mean after this. Okay, here as you can see, so in these two ways you can find the phase difference between the two quantities, right? So usually if the alternating quantity is starting at the 0 point, then we usually represent, because this is a sine wave, so V of t is equal to Vm into sine omega t, because here let us consider here it is theta. Okay, or in other words here omega t plus 0 actually, because here it is starting at 0, and but current is started before than these 0 degrees. Okay, and the phase difference between these 2 points is phi, so that here the I of t, that is Im sine omega t plus this phase angle, and the difference between these two quantities, here it is the phi. So this is the phase difference between the two quantities. And then how this phase difference will happen? I mean, it depends on what kind of factors, right? So let us consider here, mainly here the phase angle or the phase difference between the two quantities is depends on the nature of the load. So here we have considered the three different types of loads. The first one is the resistive load, another one is the inductive load, another one is the capacitive load. Let us consider here this is a pure inductive, pure capacitive, and pure resistive load. So of course here in case of pure resistive load, okay, so the phase difference between the voltage and current is 0, because here the voltage and currents are starting at the same point, so there is no phase difference, and the difference between the peak values and the difference between the starting points is same. So then here the phase difference between the voltage and current, okay, when the load is pure resistive, then here it is 0. So that's why here the Vm and Rm sin omega t is both are 0. Okay, or in another words we can say here the unity power factor, because here the phi what is that, here the phi is 0. Okay, the power factor is nothing but here it is cos phi. Okay, so cos 0 is equal to 1. So here cos phi is the power factor. So that's why here we can say it is a unity power factor, because the cos phi value is 1, because of the phase difference between these two quantities is 0. Then if you go for the inductive circuit, okay, or the load is pure inductance, then the phase difference between the voltage and current is 5 degrees, because here the current, okay, lagging the voltage by 5 degrees. the current lagging the voltage by 5 degrees, because then here it is a concept of lagging and leading. Okay, so if you observe clearly, here voltage is starting at this point. Okay, after 5 degrees here the current is starting, so which means here it is lagging behind the voltage. Okay, then how much it is lagging? Here it is the difference between these 2 points. Let us consider it is 5. Then the current is lag behind the voltage by 5 degrees. So that's why here we can say it is a lagging power factor, because here the phi having some value. Okay, so that's why here it is a lagging power factor. And we can say here, of course, here also the same voltage equation. Here it is voltage again, V of t is equal to Vm sine omega t. Okay, but the current equation here it is, of course, then I of t is equal to I sine omega t minus phi, because here it is current is lagging. In the previous case it was leading, so that's why here it was a plus phi, but here it is lagging, so that's why minus phi. Then when coming to the capacitive load here, in the capacitive load, as you can see, the current leading the voltage by 5 degrees, because here the voltage is start, because here we are taking the voltage as a reference, because in these 3 cases the voltage is starting at the 0 point, but the current is starting at different points. Of course, in the case of pure resistor, both are starting at the same point, but in case of pure inductor, the current is lagging behind the voltage by 5 degrees, but in case of pure capacitor, here the current leading the voltage by 5 degrees. Okay, because let us consider the difference between these two is 5. So that's why here it is plus 5, because here it is leading, the current is leading than the voltage V of a 5 degrees. So that's why here of course, let us consider IC of t, because the capacitive current. So IC of t is equal to IC sine omega t plus 5. So this is how the concept of phase and phase difference and lagging and leading, okay, and the power factor and all. Okay, so from this concept we can understand 3 different terms. What is mean by the phase, and how to, and what is the phase difference, okay, and what is mean by leading and lagging. Okay, when we can say, in both ways we can say here, if suppose if you take voltage as a reference, then here the current lags behind the voltage by 5 degrees in this case. Okay, or in other words, the voltage is leading 5 degrees, okay, with respect to the current, because here the voltage is leading with respect to the current, but the current is lagging with respect to the voltage, right? So both ways we can say. Then let us, because this is this circuit is in the single phase, okay, but when we go for the 3 phases, as we know, in the 3 phase, the phase difference between each phase is 120 degrees, because each phase is distributed at an 120 degrees with each other. So then here, as you can see, suppose let us consider in the 3 phases, okay, or RYB or RBG, or we can say ABC, whatever it may be the notation. So in the 3 phases, 3 voltages and the 3 currents are there, okay, which means phase voltage, phase A, phase B, phase C, and the phase, even the current also phase current and line current, and in the voltages also phase voltages and line voltages that we know. So let us consider, okay, irrespective of the phase or line, here there are 3 various quantities are there. Let us consider these are the 3 phase voltages. Then the first voltage, let us consider here VR here it is starting at the 0, okay, but when you see the VB here it is starting at here, okay, so V blue, and then VG is starting here, so which means here VB is lagging behind the VR at an angle of phi 1, but VG is leading at an angle of phi 2 with respect to the VR, right? So here VB is, because here it is minus, so that's why lagging, and here it is plus phi, so this is leading. So here VB is lagging with respect to VR, and VG is leading with respect to VR, right? So this is how we can represent, or we can write the voltage or the current equations by considering the phase difference between the 2 quantities. So this is how the concept of phase angle, and the phase difference, and leading and lagging. Then coming to the power factor. So here this power factor is majorly depends on the same, the phase difference between the 2 quantities, okay. Or in another words here, this power factor can be easily defined by using the power triangle. So here, this triangle we usually call it as a power triangle. In the power triangle, here this adjacent side here it is the active power, and the opposite side is the reactive power, and the hypothesis is the apparent power, right? So then the angle between these hypothesis and the what is that the side here it is the adjacent side here it is 5 degrees, and this phi is the phase difference between these two. And when coming to the power factor, here it is represented as a cos phi. Here phi is the angle between the apparent power and the active power, right? So we know already what is meant by the active power, what is meant by the reactive power, and what is meant by the apparent power. So in another terms, apparent power is nothing but the total power. So because the total power here, the apparent power is represented as a S. Okay, then the total power is actually here the sum of the active power and the reactive power. Okay, because these are the complex terms. Or in other words, we can write P plus JQ. So or we can write simply S square is equal to P square plus Q square. Okay, and in other words, here the total power or the apparent power S is equal to square root of P square plus Q square. So here P represents the active power and Q represents the reactive power. We know already, what is active and reactive power, that we have already discussed. So active means here it is the useful power, actually utilizing power, here it is the active power. Then here the power factor is the ratio of the working power measured in kilowatts, okay, to the apparent power measured in the kilovolt ampere. Okay, kilovolt ampere. So here it is kW, kilowatts, and kilovolt ampere. So here this is, which means here it is measured by the the ratio of the power measured to the apparent power measured. So here it is apparent, which means here VI cos phi, which means actually P by S. Okay, P is equal to VI cos phi by, here it is VI. So VI gets cancelled. Then here it is the power factor which is equal to cos phi. So the power factor is nothing but the ratio of the apparent power, the ratio of the active power by the apparent power. So this is called the power factor. Next, the total power. Just now we have discussed the total power is nothing but the sum of the, or the complex sum. Okay, complex sum of the active power and the reactive power, which means here it is P plus JQ. Just now we have discussed, which is equal to S is equal to. So, or in other words, S is equal to square root of P square plus Q square. So this is about the total power of the total power. Okay, the definition of the total power. So here the total power we usually measure in terms of the watts. Then here, from this slide we can easily understand, okay, what is mean by apparent power, active power, and reactive power. Okay, what is mean by the power factor, and what is leading and logging. All these concepts that we can understand from this single slide, right? So because here the power triangle, as you can see, it is an right angle triangle showing the relation between the active, reactive, and the apparent power. So the power triangle will give the relation between the various types of powers. Okay, so that is active, reactive, and the apparent power. So let us consider here each component of the current, that is the active component. If it is a active component, then suppose if it is a current, okay. So if it is a active component, then we usually represent as a I cos phi. Okay, and if it is a reactive component, then it is I sin phi. Like that we usually represent. Okay. And suppose if it is a voltage, then V cos phi and V sin phi. So that is depends on which parameter that we are considered. So just now we have discussed the power factor is nothing but the the ratio of the active power by the apparent power. So the active power here it is P, which is nothing but here P is equal, here it is VI cos phi. Okay, and the apparent power here it is S. So S is equal to VI. Then VI gets cancelled. Then you will get the cos phi. So which is the power factor, right? So the power factor is also, the power factor can also defined as the cosine of the phase angle between the voltage and current. Here, because of course here in the power triangle the phi is nothing but the the angle between the apparent power and active power. Okay, but actually the phi, the cos phi means here the phi is the phase difference between the voltage and current of a particular quantity. So, and of course whether the power factor is, whether the the phase angle is leading or lagging, it depends on the type of the load that we are considered in a particular application. So because just now we have discussed, if it is a pure resistive load, then the power factor is unity, and if it is a pure inductive load, then that is a lagging power factor you will get, and if it is a pure capacitive load, then we will get a leading power factor. Okay, so like that we can understand what is mean by lagging, leading, and all these. Next, because here just now we have seen, the total power is nothing but the complex sum of the the active power and the reactive power. So which means what is mean by these complex and what is the notation of the rectangular form and the complex form. So here that we can see here the various various types of representation, because here these alternating quantities, as we know, before we have discussed about the DC quantities, the direct current are, the DC quantities are having both polarities and the magnitude, but in case of alternating quantities having the direction and the magnitude. So that's why here there is a concept of these rectangular notation and the polar notation. So because because here the AC waveforms are represented in the form of sinusoidal, so the sinusoidal expression in terms of the phase are right. So that's why here it is important to know how to convert the complex into polar, or polar into rectangular form from each other. So we know already the rectangular, or we can also call it as a complex form. So that is x plus or minus z into y. So which means here the x is the real term and j is the imaginary term that we usually called. And if it is a polar form, then we can represent the same quantity in the polar form or at an angle of plus or minus theta. Then here, how to find r and theta? So here the r, we can find r is equal to square root of x square plus y square, and here theta is equal to tan inverse y by z. So y by x here, right? So which means once you know the x and y values, then we can convert this rectangular form into polar form. Right. So how we can convert the polar form? Because if you want to convert the polar form, we need to know the value of the r and theta. So the r value, that we can know the square root of x square plus y square by substituting in this equation, and similarly the theta value also we can get by substituting in this equation. Then another form is there, but this is very rarely used. But these are the two very important. Are the mostly we use these two kind of forms only. Either it is a rectangular or the complex form, or the polar form. But there is another form, that is trigonometrical form. So that is z is equal to r into cos theta plus or minus j sin theta. And another form is also there, exponential form. Very rarely we use. This is r e to the power of plus or minus j theta. So in this case also here r is same, like r is equal to square root of x square plus y square, and theta is equal to again the same way. Theta is equal to tan inverse y by z. Okay, so just now I have mentioned. And another one, suppose if you are having a polar form, then how we can convert into the rectangular form? So in case of x is equal to r cos theta, because you know the value of r and theta, then you can substitute, then you will get the x value. And similarly y also you can get, so y is equal to r sin theta. So then if you substitute r value and theta value in this equation, then you will get x and y values, so that you can convert the polar form into the rectangular form. So this is how the polar form representation and the rectangular form representation, and also we have seen the trigonometrical form and the exponential form also we have seen. And now we know how to convert so one form of quantities into another form, which means either complex to polar or polar to complex, and similar way the exponential. So in one form of quantities to another form. Then another important thing here, it is the Fleming's right hand rule. So these Fleming's left hand and right hand rule we have already discussed in a concept of self and mutual inductance principle, or the Faraday's law of electromagnetic induction. So from there we have already seen, okay, what is mean by the mutual inductance and what is mean by the self inductance. Of course, here also again we will discuss what is mutual inductance and what is self inductance. So before going to that, here the Fleming's right hand rule. Okay, actually what the Fleming's right hand rule, what is that mentioned here? So as you can see here in the picture, the same like here, if you can put your right hand like this, okay, which means here the three fingers they placed the perpendicular with each other. So like this here, this is the thumb, okay, and this is the forefinger, and this is the middle finger, right? Okay. So here, what is this thumb represents in the Fleming's right hand rule? Okay, in the thumb represents the direction of the force, okay, which means the direction of the force means here, suppose if you take in a motor or generator concept, okay, the direction of the force means here it is a rotating force, okay, in which direction, whether it is a clockwise or anti-clockwise. So here it represents the direction of the force, and this forefinger here it represents the direction of the field, okay, which means here in these three, if you know any one of the direction, okay, then the two other directions that we can find, because here if you know the direction of the field, then place this middle finger as it is, whatever the direction of the field here it is. So here let us consider the direction of the field is from right side to left side. Then here I have placed this finger, I mean this right hand, I mean this finger is same like that. So that which means here the direction of the force here it is like this, and the direction of the current flowing through this coil E here it is in this direction. Otherwise, if you want to make it is in opposite direction, then in this way. Okay, if the direction of the here it is, because here it is towards I mean the direction of the current is towards us, okay, but if you place here it is like this, okay, then the direction of the the direction of the force here it is other way, okay, and this is outwards, and here it is the downwards, okay. So which means here if you know any one of the direction, either it may be force direction, okay, whether it is moving upward or the downward, okay, and on another one here this forefinger is representing the direction of the field, okay. So if you know the field, then we can know other two directions, or if you know the current that is flowing through the coil, then we can know the field direction and the force direction. So this is how the Fleming's right hand rule. So as they mention here, as you can see, the right hand held with the thumb, okay, the indexing finger and the middle finger, okay, sometimes this is a forefinger or the indexing finger, and this is the middle finger, okay. Then here finger mutually perpendicular to each other, and as shown in the diagram, and the thumb is pointed in the direction of the motion of the conductor, okay, which means that's what here the force or the direction of the motion of the conductor, and related to the magnetic field. So this is how I mean we can find any, if you know any one of the direction, then we can find the other two directions by using this Fleming's right hand rule. Then finally, the self-inductance and the mutual inductance, the concept of self and mutual inductance. Of course, the self and mutual inductance is depends on Faraday's laws. So here, the self-inductance, okay, so which means, as we know already, the concept of EMF, okay, the electromagnetic force, okay, how the EMF will generate in a particular coil, okay, then when EMF is induced in the same circuit, then that is called it as a self-inductance, okay. And if the EMF is induced, okay, and are the flux produced by the conductor is linking with the another conductor, so due to that an EMF is induced in the another conductor, then that is called as the mutual inductance, right? The self-inductance and the mutual inductance. So that's why here you can see in this diagram the self-inductance here it is whatever the field, okay, or the field, okay, or the flux produced by this particular coil is, okay, linking with itself. So that's what here it is the self-inductance. And in case of mutual inductance, okay, so the EMF produced by the one coil, okay, I mean or the flux produced by the one coil is linking with the another coil, so that the EMF is induced in that coil, then that is called the mutual inductance, because in the mutual inductance here we need the two coils, and here it is one coil, because here as you can see the coil A, because of the flux linkage with the coil A, it is linking with the coil B, so that an EMF is induced in the coil B, and the EMF is measured with this galvanometer. So that is how here the mutual inductance concept. So the self and mutual inductance. So this is all about the definitions and terminology from the module 2, which is analysis of the electrical circuit. So in the next class, we will discuss the next topic. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.